Hello everyone, myself P. Jitendar, Assistant Professor in Electrical and Electronics Engineering at MLR Institute of Technology, Hyderabad. So in previous video lecture, we have discussed about the superposition theorem and Thevenin's theorem. Now in today's video's lecture, I am going to discuss about the Norton's theorem. So in Norton's theorem, so the main overview of Norton's theorem is, so here the statement. So what is the statement of Norton's theorem and what is the procedure? So what is the procedure involved in the Norton's theorem and how we can verify the Norton's theorem? So these are the we need to discuss in today's topic. Okay. So here the first one is the statement of Norton's theorem. So here the statement of Norton's theorem is, in any linear or bilateral network contains two or more voltage or current sources, the total current or voltage is replaced by Norton's current and the total resistance is replaced by Norton resistance in parallel with the load resistor RL, that is load resistor RL. That is the statement of Norton's theorem. Okay. So here I will tell you once again. The statement of Norton's theorem is, in any linear or bilateral network contains two or more voltage or current sources, the total voltage or current is replaced by Norton's current and the total resistance is replaced by Norton's resistance in parallel with the load resistor RL. That is the statement of Norton's theorem. Here is the statement. So here, according to statement, here I am taking the one simple circuit. So the circuit is having two loops here. So I am taking the one simple loop. So here voltage source, I am taking voltage source as V and the resistor is R1 and resistor is R2 and here resistor is R3 and here load is RL. Now across this load we need to calculate the current. So we need to calculate the load current, that is IL. We need to find out the load current through load resistor RL. Now this main circuit, it will be converted into the equivalent circuit or equivalent Norton's circuit. So in that case, here we are having voltage, total voltage is V. So this total voltage V is replaced by Norton's current. So in the given circuit, voltage is there. So this total voltage is replaced by Norton's current, that is IN. Norton's current is IN and the total resistance R1, R2 and R3. So these total resistors are replaced by Norton's resistance, that is RN. So this is Norton resistance RN in parallel. So in parallel with the load resistor RL. So here we have to connect the load, that is RL. Now through this load resistor we need to calculate the load current IL. Okay. So here is the equivalent circuit. Equivalent circuit of Norton's theorem. Okay. So in this Norton's theorem, so we are having some procedure. So in that case, so the procedure of the Norton's theorem is, so in that case the step 1. So step 1 is, first of all we need to find out the total number of loops in a given circuit. So first we have to find out total number of loops in a given circuit. After that we have to give the current direction. So we need to give the current directions. Okay. That is step number 1. And step number 2 is, we need to short circuit. Okay. We need to short circuit load. So for example, so here we are having the circuit. So here also I am taking the same circuit here. So voltage is V, resistor is R1, R2, R3 and load is RL. So here the second step is, we need to short circuit the load resistor. So load resistor is here is the load resistor is RL. Now what we need to do? So we need to short circuit the load resistor RL. So means, so we'll get circuit like this. So we need to short circuit the load. So here load is short circuited. So across these terminals we need to calculate the Norton's current IN. So similarly, voltage is V and resistor is R1 and this is R2 and this is R3. So by calculating this circuit, we will get Norton's current, that is IN, right? That is step number 2. And step number 3, so step number 3 is we need to short circuit the voltage source and we need to remove the load. Now across these two terminals, we need to calculate the Norton's resistance, that is Rn. Okay. So here the step number 3 is we need to short circuit the voltage source and we need to remove the load resistor. Now across the given two terminals, we need to calculate the Rn, that is Norton resistance Rn. And finally, according to statement of Norton's theorem, the total voltage V is replaced by Norton's current and the total resistance R is replaced by Norton resistance in parallel with load resistor RL. Now across this load resistor RL, we have to calculate the IL value, that is load current value. Okay, that is the procedure of the Norton's theorem. Okay, so here we'll solve one circuit. So here is the question. So calculate the current through 15 ohm load resistor by using the Norton's theorem. Okay. So here in the given circuit, 20 volt voltage source is there and 6 ohm resistance is there and 8 ohm resistance is there and 12 ohm resistance is there and load is 15 ohms is there. Now across this 15 ohm resistor, we need to calculate the IL value, that is load current value. Okay. So here, so in this Norton's theorem also we are having the some steps. So here step number 1. So step number 1 is, so first of all we need to find out the total number of loops in a given circuit. So in that given circuit, the total number of loops are 2. So this is loop 1 and this is loop 2. So 2 loops means here required currents are 2. So means, so first loop is clockwise direction and second loop also clockwise direction. So both the loops are in clockwise direction. So means the first loop current I am taking as I1 and second loop current I am taking as I2. Okay. And at a 10 ohm resistor, the current is I3. So where I3 is nothing but I1 minus I2. Okay. So here current through 6 ohm. Current through 6 ohm is I1 and current through 8 ohm is I2 and current through 10 ohm is I3. I3 is nothing but I1 minus I2. So difference of I1 and I2 is nothing but current through 10 ohm resistor, right? So here is the step number 1. So step number 1, first we have to find out the total number of loops. After that we have to give the current directions. So we need to give the current direction is the step number 1. Now the step number 2 is we need to calculate the Norton's current. We need to calculate the Norton's current, that is IN. So how we can calculate the Norton's current? By short circuiting the load resistor 15 ohm. So here short circuit 15 ohm load resistor. Then find out the Norton's current. Okay. So here is the circuit. So the circuit is like this. So in this case, we need to short circuit the load. So here load is short circuited. So source is 20 volt and this is 6 ohm and this is 8 ohm and this is 10 ohm. And here load. Across load we need to find out the Norton's current IN. Okay. So here, so for the calculation of Norton's current we have to use the nodal analysis, mesh analysis, or also we need to use the Kirchhoff laws. So but here I am taking the, we can also use the series and parallel combination. So here I am taking the series and parallel combination. So in that case, first we have to find out the total resistor in the given circuit, after that total current, after that Norton's IN value, Norton's current value, that is IN through 8 ohm resistor. Okay. So here the current through 6 ohm is I1 and current through 8 ohm I am taking as I2 and current through 10 ohm I am taking as I3. Right. So now we need to calculate the total resistor first. So here the total resistance of the given circuit is R equal to, so here source is primary side, so we have to start from the opposite side. So in opposite side 8 ohm is there, 10 ohm is there. So 8 ohm and 10 ohm, these two are connected in parallel. So this parallel circuit in series with 6 ohm resistor. So means R equal to, so 8 into 10 divided by 8 plus 10 plus 6. Okay. 8 and 10 are connected in parallel, the parallel combination in series with 6 ohm. Now by calculating the R value, here we will get 10.44 ohm. That is the total resistance of the circuit. Now we need to calculate the total current. So total current means that is from the source 20 volt voltage source, that is I1. Total current I1 is equal to, according to Ohm's law, V by R. So what is V? 20 and what is R? 10.44. So here by calculating the 20 divided by 10.44 will get 1.9157 amperes. Okay. Here is the I1 value, total current value. Now we need to calculate the Norton's current by using the current division rule. So now the Norton's current through 8 ohm resistor, so that is IN. So Norton's current IN equal to, so the total current, what is total current here? I1. So I1 is nothing but 1.9157. So 1.9157 into, so 8 ohm opposite element is 10. So 8 ohm opposite element is 10 ohm resistor. So 10 divided by 10 plus 8. Here is the equation. So Norton's current IN is equal to, the total current is 1.9157 into 10 divided by 10 plus 8. And now by calculating the given equation, we will get IN value. So IN is equal to 1.0642 amperes is the Norton's current. Okay. This is the step number 2. Now here the total voltage is replaced by Norton's current IN. So IN is equal to 1.0642 ampere. So this is step number 2. Now step number 3. Step number 3 is calculation of Norton's resistance. So how we can calculate the Norton resistance? For the calculation of Norton resistance, we have to short circuit the voltage source and we have to remove the load resistor. So for the calculation of Norton resistance, so we need to short circuit the voltage source and we need to remove load. So across these two terminals we need to calculate the Norton's resistance Rn. So here is the elements. 6 ohm, and this is 8 ohm, and this is 10 ohm. Now the Norton's resistance Rn equal to, now here this side we need to calculate the equivalent resistance or Norton's resistance. So we have to start from the opposite side. So in opposite side we are having 6 ohm. Opposite side we are having the 6 ohm resistor. So 6 and 10. So these two are connected in parallel. 6 ohm and 10 ohm are connected in parallel. This parallel combination in series with 8 ohm resistor. Okay, 6 and 10 are connected in parallel. The parallel combination in series with 8. So means, so the Norton's resistance equal to 6 into 10 divided by 6 plus 10 in series with 8. Okay, so the Norton's resistance Rn equal to 6 into 10 divided by 6 plus 10 plus 8. So by solving this equation, we'll get Rn value, that is 11.75 ohm. This is the Norton's resistance Rn. Step number 3. Now step number 4. So step number 4 is, according to statement of Norton's theorem, the total voltage is replaced by Norton's current, and the total resistance is replaced by Norton's resistance in parallel with load resistor, that is 15 ohm, right? So here now we need to draw the equivalent circuit. So the equivalent circuit is, so here is the Norton's current, that is IN. Here is the Norton resistance Rn, and here is the load. So load is RL. Now across this load we need to calculate the IL value. Now IN is there. What is IN value? 1.0642 amperes is the IN value. Now what is Rn here? 11.75. 11.75 ohm. And what about the load? So load already is there. Load is 15 ohm. So RL is equal to 15 ohm. Now through 15 ohm we need to calculate the IL value. So now here also we need to apply the current division rule. So here at 15 ohm, IL equal to total current. For the given circuit, the total current is IN. So Norton's current IN into, what is the opposite element of this RL? Rn divided by Rn plus RL is the equation. Okay, so now, so IL equal to Norton's current. What is Norton's current? 1.0642. So 1.0642 into Norton's resistance 11.75 divided by Norton resistance is 11.75 plus load is 15. Here now by solving the equation, so 1.0642 into 11.75 divided by 11.75 plus 15, by solving that we will get load current IL, that is 0.4674 amperes is the load current. Load current means, so current through the load resistor 15 ohm. Okay, here is the calculation part of the Norton's theorem. Now we have to verify if it is a right or wrong. Now we have to verify by using the nodal analysis, or by using the Kirchhoff laws, or by using the mesh analysis. We can verify the Norton's theorem. Okay, so here I am taking the same circuit by using the Kirchhoff laws. So here I'm taking the same circuit. So plus minus 20, and this is 15 ohm, and here, so this is 6 ohm, this is 8 ohm, and this is 10 ohm. Okay. Now by using the Kirchhoff laws, so here I am using the Kirchhoff laws. By using the Kirchhoff laws, we need to calculate the current through this 15 ohm resistance. Okay. So for the Kirchhoff laws also, so first of all we need to find out the total number of loops. So in that case the total number of loops are 2. So this is first loop and this is second loop. So 2 loops means here the required currents are 2. So both the loops are in clockwise direction. So first loop is clockwise direction. I am taking current as a clockwise direction, that is I1, and second loop current direction also clockwise. I am taking current as I2. Now current through 10 ohm is here at this node point, current is dividing, means current through 10 ohm is I1 minus I2. Okay. After that we have to assign the polarities here. So it is starting from the positive, means here also starting from the positive. So plus minus plus minus. So here also this is plus minus, and here also this is plus minus, right? Now apply KVL. So here verification. So verification of Norton's theorem. Now in this case I am starting from this point. So when I am starting from here, always we need to take the second polarity, or we can also take the first polarity. So in that case I am taking the second polarity, that is plus 20, first loop equation, plus 20, and the second polarity of 6 ohm is minus 6 I1, and the second polarity of 10 ohm is minus 10 into current is I1 minus I2. So I1 minus I2, and there is no more elements, that should be equal to 0. Now simplify the equation. So 20 minus 6 I1 minus 10 I1 plus 10 I2 equal to 0. Now so minus 6 I1 minus 10 I1, so minus 16 I1. So minus 16 I1 means it will go that side. So plus 16 I1 minus 10 I2, that is equal to 20. Let us take as equation number 1. Here is the first loop equation, and the second loop equation. The second loop equation also clockwise direction. So in this case also I am starting from this point. I am starting from here. So when I am starting from this point, here also we need to take the second polarity. So here the second polarity of the 8 ohm is minus 8 I2, next minus 15 I2. So because these two are in series current is constant. Next the current is upward direction. Okay. So plus second polarity is plus 10 into I1 minus I2. That should be equal to 0. So simplify the equation. Minus 8 I2 minus 15 I2 plus 10 I1 minus 10 I2 equal to 0. So here 10 I1. So minus 15 I2 minus 10 I2 minus 25 I2 minus 25 I2 minus 8. So minus 25 and minus 8, 20 minus 33 I2, that should be equal to 0. Let us take as this is equation number 2. Okay. So now by solving equation 1 and equation 2. So equation 1 is 16 I1 minus 10 I2 equal to 20. And equation 2 is 10 I1 minus 33 I2 equal to 0. That is equation number 2. Now here by solving equation 1 and 2. By solving equation 1 and 2, we'll get I1 value and I2 value. So here I1 value is 1.5420 amperes and I2 value is 0.467 amperes. So these are the loop currents. But here we need second loop current here. Second loop current is nothing but I2. So I2 is nothing but current through 15 ohm. So here the current through 15 ohm is I2 or IL, that is equal to 0.467 ampere. Okay. So here in previously by using the Norton's theorem also we are getting 0.467 ampere. So you can see here 0.467 ampere load current by using the Norton's theorem, or by using the Kirchhoff laws also we are getting 0.467 amperes, right? So like this we need to calculate the Norton's theorem. Okay. So here finally we can write, hence the Norton's theorem is verified. This is the calculation part of the Norton's theorem. Okay. So in today's lecture we are discussed about the what is the statement of Norton's theorem, what is the procedure involved in the Norton's theorem, and how we can solve the problem by using the Norton's theorem, and how we can verify the Norton's theorem. Okay. So in next lecture we are going to discuss about the maximum power transfer theorem. Okay. So thank you one and all.